Alright, ladies and gentlemen, so we are starting now into 6.5, which is all about logistic growth. Alright, so the goals of this lesson and this entire topic are to review what partial fraction decomposition is. We're going to anti-differentiate partial fractions and understand why populations grow in real-world context as well. The four things you need to be able to do to be successful in this section is one, can you define and decompose partial fractions? Can you integrate partial fractions? Can you define what logistic differential equations are? And then finally, can you use logistic growth models in real-world applications? For this part 1 of 6.5, we're going to be diving into specifically reviewing and defining partial fraction decomposition. So let's look at the basic definition here. I'm not going to spend too much time on the slide. I think it'd be helpful more with an example more than anything. So partial fraction decomposition. This should not be new to us. You look at it in Algebra 2 and you look at it in pre-calculus as well. So partial fractions. Let's say, for instance, we have a function in which it is a division of two polynomials. We'll call them P and we'll call them Q. It must be a division in which P is less in degree than Q. Alright, so if the highest degree down in Q is 2, that means the degree of P has to be 1, and so on and so forth. The exponent, right? And we have to also make sure that Q of x, the denominator polynomial, can be factored out. It can actually have a distinct factor that we can look into. However you want to do your factoring, by trial and error, by box method, whatever it is. Alright, that's how we utilize it. If this is the case, we can check off that it's a polynomial and a polynomial, that the degree of P is less than the degree of Q, and that Q can be factored on out with at least two linear factors. Then f of x can be written as a sum of rational functions with actual linear denominators. So if we started with quadratics, we're going to be able to write it as a linear. If we started as cubics, we can write them as linears, and so on and so forth. Well, let's dive into an example and see where this comes into play. It says write the function x minus 13 divided by 2x squared minus 7x plus 3 as a sum of rational functions with linear denominators. So first and foremost, we need to identify, is the degree less on the top than it is on the bottom? Yes, it is. All right, the degree of the numerator 1, the degree down here is going to be 2. Now, when we're looking at these, we got to see, can Q, the denominator, be factored out nicely? Well, 2x squared minus 7x plus 3, this is going to factor out nicely to kind of save some time here. We're going to factor this on out, and this is going to end up saying that f of x also equals x minus 13. This will factor out very, very smoothly to 2x minus 1 times x minus 3, okay? Once again, you can do your own personal favorite method for factoring if you are not too comfortable with that on your own. So now what our goal is our goal is to find a sum of this. So our goal is to get to finding a value such that f of x equals a over 2x minus 1 plus another value, b, we'll call it, over the other linear factor, x minus 3. And so we have to take into account of what this actually looks like. Well, I separated this on out. So to quote-unquote get a common denominator, I would in the end have to multiply the a by x minus 3 and the b to get 2x times 2x minus 1, and that would give me back to my common denominator here. So let's say, for instance, I went ahead and did just that. I said that f of x is equal to a times x minus 3 plus b times 2x minus 1 all over 2x minus 1 times x minus 3. Well, what does this mean for us now? Well, this means that the numerator, a times x minus 3 plus b times 2x minus 1, actually, in fact, equals x minus 13, because that's what the numerator of the original function f of x actually equals. So, this leads us to show that a times x minus 3 plus b times 2x minus 1 equals x minus 13 in this example. Okay? And so let's think about how to come down to some things here. So where could we possibly, I guess, kind of go with this is, well, let's think about some possible solutions actually for x themselves. So we know x equals 3. That's going to end up giving us a value that is found in the function x equals 3, right? Because we separated it out. We saw one of the quote-unquote solutions to that denominator, x equals 3. That is going to, in turn, cause a 0, 3 minus 3 times a, which will then let us to get b by itself. So I'm going to let x equals 3 to start off with, and I get a times 3 minus 3 plus b times 2 times 3 minus 1, set that equal to x minus 13. Well, that will cancel out and become 0, and then I end up getting b times 5 equals, whoops, I'm sorry, here I did not switch out the x, and this is 3. Alright, I can now switch out, alright, to see that 5 times b equals negative 10, or that b, in this case, will equal a negative 2. Alright, and so now we have the value for b. So very similarly, on the other side of things, the solution to 2x minus 1, alright, that is going to be when x is 1/2. And so when x equals 1/2, we'll do the exact same concept here. We'll let x equal 1/2, and that's going to cancel on out b in this case. So we have a times 1/2 minus 3 plus b times 2 times 1/2 minus 1 equals 1/2 minus 13. Again, that will cancel on out. Again, we can kind of go ahead and kind of simplify this down a little bit. We get negative 5 halves times a is going to end up equaling negative 25 halves on the right-hand side. All right, we'll multiply by a negative 2 over 5 on both sides, thus seeing that a in the end gives us a positive 5 for an answer. So once we are all said and done, I'm going to write the answer up top up here. We can make the statement that f of x can also be written in the fact of a being 5 over 2x minus 1 plus, I guess we'll make it negative because it was a negative 2. I want to put a negative and a positive both in there. We'll make a minus 2 over our other denominator, x minus 3. Alright, so give that one a look through. Make sure that we're on the same page with that. One I want you to give a shot on your own. Let's take a look. This is going to be 16. So I want you to do the same concept. Turn this into a sum of rational denominators, x squared plus 3x minus 10. Same concept, write it as a sum of rational functions with linear denominators, just like we did before, okay? Just to kind of save a little bit of room, I'm going to hopefully that you see that a should equal 2 and b should equal negative 3 in the end. Alright guys, and we're on to the next one.